Hi guys, hope you are doing good today. I'm going to start a new chapter, chapter 7. In this chapter, we are talking about sampling distribution of the sample mean. So, this is some kind of collection of sample means. So, we are going to check, we are going to calculate, we are going to see what will happen if we have a sample means. Okay. Under this chapter, first section is sampling error, the need of sampling distribution. So let's see what is this sampling error mean. Sampling error is some kind of error resulting due to sample to estimate the population characteristic. You remember that we estimate population using sample. Because of that, we will be having this sampling error. Okay. Sampling distribution of the sample mean is for a variable x and given sample size can be simple n. Distribution of the variable x bar is called the sampling distribution of the sampling mean. Okay, let's consider this one. Here A, B, C, D, E. A, B, C, D, E. There are 5 samples. There are 5 samples. A equals 76, B equals 78, C equals 79, D equals 81, E equals let me check 86. Okay, those are the values in mean of each samples. Okay, these are mean of each samples. Now I am going to consider these values together. Okay, I can consider like this samples 2 by 2. First two like AB, AC, AD. Okay, two samples together, so that these are the values. A is 76, B is 78. So mean of these two is 77. If you add these two together and divide by 2. Clear? When you consider sample A and C, A value is 76, C value is 79. So mean is x bar, we denote x bar, is 77.5. Likewise, you can consider pairs. Okay, if you consider these pairs and check these x bar values, you can see like this. If you use this plot, you will see values are like this. So first value 77. So let's see where is 77. See here 77. Next value is 77.5. Okay, it is somewhere here in between 77 and 78. Likewise, you can draw these dot plots. Okay, dot plot. What is this 80? 80 is the actual mean. Okay, 80 is the actual mean. If you add these values together, 76 plus 78 plus 79 plus 81 plus 86, divide by 5, you will be having 81. Oh sorry, 80. Value 80. That is the mean. That's denoted here. Okay. Don't think about that too much. We will see what will happen if we extend this number of samples. Like if we consider ABC instead of AB, then ABD, something like this, 3 samples. What about if we consider 4 samples, ABCD, ABCE, something like that. What about if we consider just one sample like this, ABCDE? We will see what will happen. If we consider just one samples, ABCD, so you can see the x bar values are their values 76, 78, 79, because here individual samples 76, 78. So you can see values here 76, this value is 78. Okay, same as ABC values, ABCD values, CDE values. Okay, the second one is the mentioned in here, this one last page. Third one is n equals 3, which means a b c, a b d, likewise, and get the uh, mean of these 3 samples, something like that. So if you extend this up to, since there are 5, you can extend this up to 5. So you can see that from here to here, this variation of this means is converging. See, variation of this means are converging. When you increase the sample size, see, start from 1, then 2, 3, 4, 5, this variation or this mean come into a one number, right? It's converging, it's come to 18. So this is the idea behind this, why we consider this sample a mean of sample means. Sample size and sampling error. When we increase the sample size, sampling error goes down. Okay, that tends to be in estimating population mean. So we are talking about population mean mu denoted by the population mean. So we can estimate population mean mu by sampling mean x bar. X bar is the sampling mean. Okay, mean and standard deviation. Let's see what will happen in this sample mean, standard deviation and mean. For large size samples, mean variable of x bar is equals to the mean of the population. So mean of x bar we denote by mu x bar is equals to the population mean. Standard deviation of this x bar is equals to standard deviation of population divided by square root of n. This is standard deviation of population. Okay, let's check this example. Mean living space of single family detached home is this much. So they have given mean living of single family. So this gonna be what? This gonna be mu, population mean. Okay, assume a standard deviation this much. This gonna be sigma, population standard deviation. Okay, now we consider sample 25 and they ask mean and standard deviation of x bar. So this mean of x bar, mu x bar equals to, from previous slide, it doesn't matter about the sample size, mean of the mean sample or mean of the x bar, equals to population mean, which is mu. So mu equals to 1742, and standard deviation sigma x bar equals to sigma over square root of n. It depends on size of the sample. So what is sigma here? 568 divided by what is square root of n? N is 25. So 568 divided by 5. Okay. Now we have to in part B we have to repeat this first section for sample size 500. So mean of x bar equals to mu. It doesn't change because of the sample size 42. Yeah, but sigma x bar, which mean standard deviation of x bar, is sigma over square root of n. Sigma doesn't change, but n change. Here it is 500. Okay, so standard error decreases when sample size are increases. Key facts: the larger sample size, smaller standard deviation. Smaller standard deviation of x bar more closely to the possible value of x bar. Cluster around the mean x bar. Mean of x bars equals to the population mean. Mean of x bars equals to the population mean, mu. Okay. Okay. Let's check what is the sampling distribution of the sample mean. Sampling distribution of the sample mean for a normally distributed variable. What is normal distributed variable? We have done this in chapter 6, normal distribution. Suppose a variable x of a population is normally distributed with mean mu and standard deviation sigma. So x distributed normally, mean mu and standard deviation sigma. Okay, this is how we write normal distribution in general. Okay, the sample size is n. Variable x bar is also normally distributed. So x bar again normally distributed with mean mu and standard deviation become sigma over square root of n. This is what they have mentioned here. The relationship between x and x bar. So when you check these shapes, this is perfectly bell shape, normal distribution, this normal curve, mean 100, standard deviation 16. Here mean 100 but standard deviation become 8. Here mean 100, standard deviation is 4. You can see that when standard deviation becomes smaller and smaller, okay, standard deviation becomes smaller and smaller with the size of the sample, the peak goes up, peak is increasing. Okay, okay, this is the last thing in this chapter, central limit theorem, CLT, central limit theorem. This is a, I would say, a giant theorem in statistics. We use this theorem a lot. So what is this says? Central limit theorem says relatively large samples, for relatively large samples the variable x bar is approximately normally distributed. So we can consider for large sample sizes variable x bar is approximately normally distributed regardless of the distribution of the variable. It doesn't matter about the variable. If we have large enough sample size, distribution of x bar is approximately normal distributed. It becomes better and better when we increase the sample size. So as you can see here, for 1000 samples, this looks like normal curve, normally distributed. Okay, when you increase 10,000, 1 million, it looks like perfect bell shape, perfect normal distributed. Okay, that's what we that's why we use central limit theorem. Okay, sampling distribution of sample mean. Suppose that our variable x population has mean mu, standard deviation sigma for size n. What is the population mean? What's the mean of x bar? Mean of x bar is equal to population mean. Okay, standard deviation of x bar is sigma over square root of n. Population standard deviation over square root of n. If x is normally distributed, then x bar regardless of the sample size normally distributed. Okay, if x is normal distributed, x bar is normally distributed regardless of sample size. In any case, sample size is large enough, then x bar we can approximate to normal distributed. Okay, sample size is large enough, then we can approximate x bar to a normal distributed. So these two are really important. First one based on x is normal distributed, then x bar is normal distributed. If we have a large enough sample size, then x bar has approximately normally distributed. Okay, x bar has approximate normal distribution. Okay, so please try to understand these two situations. In the second situation, they haven't mentioned anything about x. We don't know whether x is normal distributed or not in this second step. Okay, these two are really important. Okay, let's check this one. Variable IQ is normally distributed with mean 100. Okay, mean 100, standard deviation 16. Obtain the sample distribution of sample mean for sample of size. Okay, IQ variable is normally distributed. Done. Normally distributed. Then it doesn't matter. Distribution of x bar is also normally distributed with mean, same mean. What about standard deviation? It should be population standard deviation over square root of n. So this becomes x bar distributed normally, mu which means 100, sigma it is 16 over sample size is 4, square root of 4. Okay, you can actually reduce this you can reduce this. X bar has a normal distributed 100, this becomes 2, so it's 8. Okay, so next one, distribution when sample size is 16. So it doesn't matter about the sample size. When original variable which means population is normal distributed, then x bar also normal distributed, mu sigma over square root of n. So now x bar n mean 100, it doesn't change, but sigma it's change. It's changing 16 over now square root of 16. Okay, which mean x bar has normal distribution, mean 100, this become 4 times 4. Okay, so this is how we deal with these two, especially these two concepts. Okay, okay, that's the end of this chapter. Try to solve problems as much as you can.